Metal alloys are engineered metallic systems in which controlled additions of one or more elements modify the crystal structure, phase constitution, microstructure, and ultimately the properties of a parent metal. From ancient bronze to modern nickel-based superalloys and high-performance titanium and aluminum alloys, alloy development has been central to technological progress. Alloy performance is governed not simply by chemical composition, but by solid solution strengthening, phase transformations, precipitation, grain refinement, thermomechanical processing, and heat treatment. An alloy is a metallic material containing two or more chemical elements, at least one of which is metallic. Alloying is fundamentally an exercise in controlling structure and properties. Relatively small compositional changes can alter phase stability, defect mobility, corrosion behavior, strength, ductility, conductivity, and thermal stability. Consequently, commercial alloy specifications generally define not only chemical composition, but also product form, processing condition, heat treatment, and mechanical property requirements. The modern understanding of alloys is rooted in physical metallurgy, particularly the relationships among composition, thermodynamics, kinetics, microstructure, and properties. Standard materials science treatments emphasize phase diagrams, diffusion, dislocations, strengthening mechanisms, phase transformations, and processing as interconnected aspects of alloy behavior. Historical development of alloy technology. Alloy metallurgy predates modern scientific understanding by thousands of years. Bronze, principally a copper-tin alloy, represents one of the earliest intentionally produced engineering alloys and provided harder and more useful tools than copper alone. Brass, primarily copper-zinc, subsequently became important because it combined strength, corrosion resistance, machinability, and attractive appearance. The development of iron metallurgy eventually displaced bronze for many structural applications and established ferrous metallurgy as the foundation of industrial civilization. The Industrial Revolution accelerated the development of cast iron and steel. Control of carbon content and later additions of chromium, nickel, manganese, molybdenum, vanadium, and other elements enabled steels with systematically tailored strength, hardness, toughness, hardenability, and corrosion resistance. The 20th century then produced a remarkable expansion of non-ferrous alloys, particularly lightweight aluminum and titanium alloys, and high-temperature nickel-base superalloys. A major conceptual advance was the recognition that alloy properties could be controlled through microstructure rather than composition alone. The discovery of precipitation, hardening in aluminum-copper alloys, associated with the development of duralumin, established a foundation for modern age-hardening alloys. Subsequent studies by Guinier and Preston established the structural basis of the nanoscale Guinier-Preston zones responsible for early-stage precipitation strengthening. Fundamental classification of alloys. Alloys are broadly divided into ferrous and non-ferrous systems. Ferrous alloys are based primarily on iron and include carbon steels, alloy steels, stainless steels, and cast irons. Non-ferrous alloys include aluminum, copper, nickel, titanium, magnesium, zinc, tin, and precious metal-based systems. At the atomic level, alloying elements may form substitutional or interstitial solid solutions. In substitutional alloys, solute atoms replace atoms of the solvent lattice, as in copper-zinc-brass. In interstitial alloys, smaller atoms occupy interstitial positions. Carbon in iron is the classic example. The resulting strengthening can arise through several mechanisms. Solid solution strengthening results from lattice strain, generated by solute atoms. Grain refinement increases strength through the Hall-Petch relationship, established independently by Hall and Petch. Precipitation strengthening occurs when finely dispersed second phases obstruct dislocation motion. Additional strengthening mechanisms include work hardening, transformation hardening, and ordering. These mechanisms demonstrate why the processing structure-property relationship is central to metallurgy. Two alloys with nominally similar compositions can possess substantially different properties because of differences in grain size, precipitate population, phase distribution, texture, and defect density. Ferrous alloys. Carbon and low alloy steels. Steel remains the most important engineering alloy family because it combines strength, toughness, manufacturability, weldability, availability, and relatively low cost. Conventional steels contain iron and generally less than approximately 2 weight% carbon, together with manganese, silicon, and, depending on grade, chromium, nickel, molybdenum, vanadium, tungsten, or other elements. Carbon content strongly influences hardness and strength, whereas heat treatment provides extraordinary control over microstructure. Austenitization followed by controlled cooling can produce ferrite-pearlite, bainite, or martensite, while tempering modifies the properties of hardened martensite. Representative grades include a 36 structural steel, 1018 low-carbon steel, and 4140 chromium-molybdenum alloy steel. Steels are used in buildings, bridges, pipelines, automobiles, pressure vessels, machinery, tools, gears, shafts, and fasteners. Their technological importance derives not from one exceptional property, but from the ability to produce an enormous range of property combinations. Stainless steels. Stainless steels contain sufficient chromium to establish a protective chromium-rich passive oxide film, with typical commercial compositions containing at least approximately 10.5 weight% chromium. Austenitic, ferritic, martensitic, duplex, and precipitation-hardening stainless steels provide different combinations of strength, corrosion resistance, weldability, and phase stability. Type 304 is a general-purpose austenitic grade, whereas 316 contains molybdenum and offers enhanced resistance to chloride-containing environments. Ferritic 430, martensitic grades, and precipitation. Hardening 17-4. pH expand the range of mechanical and corrosion properties available. Stainless steels are essential in chemical processing, food equipment, medical devices, architecture, transportation, energy systems, and consumer products. Cast irons. Cast irons contain substantially more carbon than steels, typically above 2 weight%, together with significant silicon. Their high carbon content promotes fluidity and castability, but generally reduces ductility. Gray, ductile, white, and malleable cast irons differ primarily in carbon morphology and matrix structure. Engine blocks, brake components, machine bases, pipes, housings, and heavy machinery remain important applications. Non-ferrous engineering alloys. Aluminum alloys. Aluminum alloys provide low density, good corrosion resistance, high specific strength, and excellent manufacturability. Major alloying systems include aluminum-copper, aluminum, magnesium, magnesium-silicon, and aluminum, zinc-magnesium. The 2000, 5000, 6000, and 7000 series are particularly important. 6061, the aluminum, magnesium silicon, is a versatile structural alloy with good weldability and corrosion resistance. 7075, aluminum zinc magnesium, offers substantially higher strength and is widely used in aerospace. Aluminum-copper alloys historically demonstrated the power of precipitation hardening, in which metastable precipitates impede dislocation motion and substantially increase strength. Modern studies continue to establish quantitative relationships between precipitate structure and mechanical behavior in an aluminum-copper systems. Copper alloys. Copper-based alloys include brass, bronze, and copper-nickel. Brass is predominantly copper-zinc, bronze is traditionally copper-tin, and copper-nickel is based on copper-nickel. These alloys combine useful conductivity with corrosion resistance and mechanical strength. Brass is widely used in fittings, valves, musical instruments, electrical hardware, and precision machined components. Bronzes are important in bearings, marine components, wear-resistant parts, and architectural applications, while copper-nickel alloys are particularly valuable in seawater service. Titanium alloys. Titanium alloys occupy an important position where high specific strength, corrosion resistance, and biocompatibility are required. Ti6Al4V, containing approximately 6 weight% aluminum and 4 weight% vanadium, is the dominant commercial titanium alloy and is used in aircraft structures, chemical processing equipment, orthopedic implants, and other demanding applications. Titanium metallurgy is strongly influenced by alpha and beta phase stability. Aluminum stabilizes the alpha phase, whereas vanadium stabilizes beta, allowing heat treatment and processing to produce controlled alpha/beta microstructures. Magnesium alloys. Magnesium provides exceptionally low density and is therefore attractive for lightweight structural applications. Alloying with aluminum, zinc, manganese, calcium, rare earth elements, and other additions improves strength, creep resistance, and processing characteristics. Applications include automotive components, aerospace structures, electronics housings, and emerging lightweight structural systems. Nickel-based superalloys and extreme temperature materials. Nickel-based superalloys represent one of the highest achievements of alloy design. Their compositions may contain chromium, cobalt, aluminum, titanium, molybdenum, tungsten, niobium, tantalum, and other refractory elements. Their exceptional high-temperature strength derives from a combination of solid solution strengthening, grain boundary engineering, and precipitation of ordered gamma prime or related strengthening phases within the gamma-N I matrix. Alloys such as Inconel 718, Inconel 625, and Rene family superalloys are used in aircraft engines, gas turbines, chemical processing equipment, and power generation systems. Their ability to resist creep, oxidation, and mechanical degradation at high temperatures makes them essential for turbine components operating under severe thermomechanical conditions. Modern superalloy production may involve vacuum melting, directional solidification, and single crystal casting to minimize deleterious grain boundary effects. Computational and atomistic modeling is increasingly being used to understand phase stability, defect behavior, and deformation mechanisms in these complex alloys. Specialty alloys. Refractory metal alloys based on tungsten, molybdenum, niobium, and tantalum provide extreme temperature capability, but are limited by oxidation, processing difficulty, cost, and, in some cases, room temperature brittleness. Lead, tin, and antimony-containing alloys historically served as solders, bearing materials, and low-melting alloys. However, environmental regulations have substantially reduced the use of lead and cadmium in consumer applications. Babbitt alloys remain important for bearing surfaces because their multiphase microstructures provide low friction and conformability. Precious metal alloys, including gold-silver, gold-copper, silver-copper, and platinum group metal systems, are important in jewelry, dentistry, electrical contacts, and specialized chemical applications. Processing, heat treatment, and future directions. Modern alloy design increasingly treats composition and processing as inseparable variables. Casting controls, solidification structure. Forging, rolling, and extrusion refine grains and introduce texture. Powder metallurgy enables compositions and microstructures difficult to obtain conventionally. And additive manufacturing permits geometrically complex components with highly non-equilibrium microstructures. Heat treatment remains equally important. Annealing, solution treatment, quenching, tempering, and precipitation aging manipulate phase fractions, defect populations, and precipitate distributions. Consequently, commercial alloy designations often specify both composition and temper or heat treatment condition. Future alloy development is moving toward computational alloy design, high entropy and compositionally complex alloys, additive manufacturing, reduced dependence on critical elements, improved recyclability, and alloys designed simultaneously for mechanical performance and environmental sustainability. Recent research demonstrates that deliberate control of chemical and structural order can generate unusual combinations of strength and functional properties, extending alloy design beyond traditional dilute systems. In conclusion, metal alloys represent the culmination of centuries of empirical metallurgy and increasingly sophisticated physical understanding. Bronze and brass established the principle that alloying could improve the performance of metals. Steels transformed industrial civilization. Aluminum and titanium enabled lightweight structures. Stainless steels revolutionized corrosion-resistant engineering. And nickel superalloys made modern high-temperature propulsion possible. The central lesson of modern physical metallurgy is that composition, processing, microstructure, and properties cannot be considered independently. The most successful alloys are those in which atomic-scale chemistry, phase transformations, microstructure, manufacturing, and service environment are deliberately integrated. This processing structure-property paradigm remains the foundation for both established alloy systems and the development of next-generation metallic materials.